Okay, we've increased the lift of our valves and increased the flow, but now we need to be able to supply air to the valve fast enough to take advantage of that increased flow. When a higher lift cam is installed, the valve may no longer be the most restrictive part of the system. The air cleaner, carb, or throttle body, the intake port, the exhaust port, and the exhaust system also play a part in restricting the flow. That's why we consider a performance high flow air cleaner and performance exhaust to be a prerequisite anytime a performance cam is installed. They're easy to install, yet they yield significant increases in performance and help the camshaft to achieve its full potential. Depending on the size of the engine, a bigger carb or throttle body might also be in order. Another way to make the most of a high lift cam is to have the cylinder heads ported to increase the amount of air the intake ports can deliver and the amount of exhaust the exhaust ports can expel. Since all the valve train parts are moving farther with a higher lift cam, the components have to accelerate more quickly and move faster, resulting in more stress on the parts, accelerated wear, and increased valve train noise. This is generally not a problem with bolt-in cams, but can certainly be an issue with very high lift cams. Really high lift cams may also exceed the design geometry of the stock rocker arms and exert a lot of side thrust on the valves at maximum lift. For any camshaft over 585 lift, we recommend that the stock rocker arms be replaced with roller rockers. The roller on the rocker arm tip reduces valve tip wear as well as side thrusting on the valve stem. However, the additional cost of a set of roller rocker arms may be a factor in deciding between a bolt-in cam or a high lift cam. There are applications where going for maximum possible lift isn't the best idea. For example, when we were developing our 551 touring cam set, we could have designed it with a 585 lift and still it would bolt into a stock engine. But since this cam was intended for touring applications, which is all about going the distance, we opted for a slightly lower 550 lift. The goal was to reduce valve train noise and to improve valve train life. Nailed it both times. It may seem like I'm trying to talk people out of using high lift cams, but that's not the case. However, you should be aware of the downsides as well as the possible gains. Luckily, lift is not the only tool we have to increase performance. So let's move on to the all-important subject of valve timing. Two valve timing events that we'll be mostly concerned with will be valve opening and closing times. S&S and the majority of the Beechman industry considers a valve to be open or closed when the tappet is 53 thousandths from its lowest point of travel, or to put it another way, off the base circle of the cam. According to historical urban legend, that's because there was enough flex or deflection in the early pushrod valve trains that it took as much as 53 thousandths of tappet lift before the valve would actually start to move on opening, and the valve could actually be closed 53 thousandths before the tappet was on the base circle of the cam. We're not entirely sure that's true, but it makes a great story. Not all manufacturers use the 53 thousandths measurement. You may see opening and closing times specified at 50 thousandths or even 20 thousandths. Automotive cam timing events are sometimes specified at as little as 5 thousandths tappet lift. So if you're comparing cam specs from different manufacturers, be sure you know how they're arriving at their numbers. Now that we have a handle on valve opening and closing times, let's look at the other two big three specifications: intake closing time and intake duration. These are two very closely related events, so we really need to look at them together. Let's start with the intake closing time spec. Intake closing time is related to duration because it actually plays a part in determining duration. Closing the intake valve later in the cycle increases duration. In general, a cam with a longer intake duration will have a later intake closing time, but not always, as we will see. Duration is defined as the number of degrees of crankshaft rotation that a valve is open. It's determined by the point when the intake valve opens and the point when it closes. The earlier it opens and the later it closes, the greater the duration. Conversely, the later it opens and the earlier it closes, the shorter the duration. As I mentioned earlier in the first video, duration is not measured in time but in degrees of crankshaft rotation. So what is the effect of duration? So let's go back to the sink for an illustration. If I open the valve, some water comes out. If I leave the valve open longer, I get more water. If some is good, more is better, right? That kind of thinking will almost always get you in trouble. It may be true up to a point, but that point depends on the engine and the application. Now that we've defined intake closing time and duration, we can talk about how they affect performance. Let's take a look at this example. The piston is just about to top dead center on the exhaust stroke. Exhaust stroke? Aren't we talking about intake timing? We are indeed talking about intake timing, but it starts at the end of the exhaust stroke. You'll notice that the intake valve is already starting to open. During this part of the cycle, the intake and exhaust valves are both open. This is called overlap. Why are both the intake and exhaust valves open? Intuitively, it may seem like this would be a bad thing. Here's why it's not. First, we have to remember that this all happens very quickly. If you're putting down the road at 2,500 RPM, that piston is going up and down almost 42 times a second. And we need to start the opening process in time to have the greatest lift occur at the most advantageous time. The other thing to realize is that when the engine is running, it isn't just the piston sucking air into the cylinder and pushing exhaust out. We also need to understand the role of the air and exhaust gases moving in and out of the engine at high velocity. Back to the overlap condition. This begins towards the end of the exhaust stroke, and by this point, the exhaust gases are moving very fast out of the exhaust port and out of the exhaust pipe. Here's where mass and velocity, also known as inertia, come into play. The exhaust gases have mass, and since they are moving out of the exhaust pipe, they also have velocity. And like any matter in motion, the exhaust gases will continue to flow in the direction they're moving until something stops them, in accordance with Newton's first law of motion. Eventually, the burned gases in the chamber will be exhausted, but the gases in the exhaust pipe keep right on moving out the pipe. It would be rude to say the pipes suck, but the exhaust gases rushing out of the exhaust pipe do create a vacuum in the combustion chamber. And since the intake valve has just opened, that vacuum starts to draw fuel and air into the combustion chamber before the intake stroke even starts. Stock camshafts will have very little or even no overlap to reduce hydrocarbon emissions. The lack of overlap reduces the possibility of any unburned gasoline in the new charge being drawn all the way through the combustion chamber and out the exhaust pipe by the escaping exhaust gases. The piston reaches top dead center and starts down the cylinder on the intake stroke. The exhaust valve closes and the vacuum created by the moving piston continues to draw air and fuel into the cylinder. The piston passes bottom dead center, or BDC, and starts to move back up in the cylinder. Notice that the intake valve is still open. How come? The piston is going up, so it can't still be drawing air into the cylinder. Common sense would suggest that the piston should be pushing the air back out. Again, we need to realize that in a running engine, this all happens very fast. The fact is that even though the piston has reversed direction, when the engine is at speed, air is still flowing into the cylinder. Not so much at idle or starting, but certainly at higher RPM. How does that work? Again, air is composed of matter and it has mass. So if you get it moving in a certain direction, like into your intake port, inertia will keep it moving in that direction until something stops it. Be assured that something will eventually stop it, but for a little while, that air continues to flow into the cylinder, giving us additional cylinder fill. Bonus, more air, more power. It stands to reason that the faster the engine is turning, the faster the air will be moving in the intake tract. So the harder the air will be to stop and the longer it will continue to flow. So you can continue to fill the cylinder for a longer time, as long as the intake valve is still open. So if your goal is to increase high RPM horsepower, a cam with later intake closing time is the way to go. For a motor that will be run at lower RPM, not so much. A long-duration camshaft with a late intake closing time is best suited for larger engines with higher compression ratios that are intended to make peak horsepower at higher RPM. Long-duration cams will normally also have an earlier intake opening time and take advantage of the vacuum that the exhaust system creates in the combustion chamber to increase cylinder fill. A drag race engine would be a good application for a long-duration camshaft. A drag racer wants high RPM horsepower to produce the highest top speed. But wait a minute, you say, isn't drag racing all about acceleration? Isn't torque what you need? The answer to that is yes, you do need torque to accelerate, but in drag racing we aren't concerned with low or mid-range torque, since drag engines aren't operated at low RPM. A drag racer comes out of the hole as hard as he or she can and never lets off until the finish line. Another reason that long-duration cams work well in high-compression engines is that they make those engines easier to turn over for starting. A high-compression engine develops a lot of pressure in the combustion chamber when the intake charge is compressed. That high combustion chamber pressure makes the engine harder to turn over during starting. At starting RPM, which is pretty low, the intake charge does not have much velocity and it's easily stopped. If the intake valve closes later in the compression stroke, some air may actually be pushed out of the intake valve during starting. That bleeds off some of the air in the cylinder before the intake valve closes, reducing the amount of air that will actually be trapped in the cylinder during the compression stroke. So the engine turns over easier. Here's a potential pitfall if you select a camshaft based on the biggest numbers. What happens when a long-duration cam is installed in a low-compression engine? Just like with the high-compression engine, air will be bled off, reducing cylinder pressure. But since a low-compression engine doesn't have much cylinder pressure to begin with, the result will be very low cylinder pressure at starting RPM. If the cylinder pressure is low enough, the engine may not even start, but it'll certainly turn over easily. This is one reason that choosing a cam just because it has the biggest numbers is not a good idea. This is sometimes called over-camming an engine. Once started, an over-cammed engine will be sluggish at low RPM because of the low combustion chamber pressure. Your bike will be a pooch off the line. At really high RPM, it may run pretty well, but the low and middle range, where you spend the most of your time riding, are going to be weak. Lower compression engines work best with shorter duration cams with earlier intake closing times. A low compression engine with a short cam generally tends to produce ample torque at lower RPM. The trade-off is the engine will not make as much high RPM horsepower. A good application for short duration cams would be a touring bike. If you need to accelerate a heavy bike up to freeway speed, pass a semi, or pull a trailer up a hill, you need low and mid-range torque. So we have horsepower cams with lots of duration and late intake closing time, and we have torque cams with shorter duration and an earlier intake closing time. Torque cams and horsepower cams are actually two ends of the camshaft spectrum and specialize in making either horsepower or torque, but not both. If you want some more of everything, a cam that falls in the middle of the spectrum, sometimes called a mid-range cam, may suit you better. Duration and intake closing times are somewhat more than stock, but they're not extreme. There is an increase in horsepower, but low-end torque is generally increased as well. Mid-range cams will not provide as much of an increase in torque or horsepower as the specialty cams, but they provide a general increase in performance across the RPM range. No one cam can do everything. If that were possible, that's the only cam we'd make. If you're looking for huge increases in low-end torque and top-end power, what you really need is a bigger motor. And rest assured, we'll have a cam for it.